Hello, once again. We'll start with the 8086 architecture. In the last lecture, we have seen some of the details related with bus, then memory related information, what is a microprocessor, and how we can do some few things related with microprocessor. So this is how the 8086 IC looks like. This particular IC will be installed on a motherboard on with which it will be accessible to many other devices. The basic purpose of this IC or any microprocessor, which is known as central processing unit, is to process, execute all the information which has been provided as an input to that device. So the information what we provide is mainly stored in memory unit. Memory unit is nothing but a primary memory and secondary memory. Primary memory is known as a RAM, whereas secondary memory is known as a hard disk. So if information is very huge, then we'll keep it in the hard disk, and that is known as secondary memory, and few part of that which needs to be processed will be fetched into RAM, and then from a RAM the information will be provided to this central processing unit. So this central processing unit is a microprocessor which has got the ability to work on the information. Let's assume that the information what has been provided from a memory is for addition. Then this arithmetic and logical unit will do the arithmetic and logical unit related information. If the information is for addition, the addition will be done. If it is subtraction, subtraction will be done. So under this arithmetic, we have addition, subtraction, multiplication, division kind of operations. Whereas in logical unit, we have AND, OR, NAND, NOR kind of operations, which can be very easily executed in this particular unit known as arithmetic and logical unit. But some of the instructions which are used for generating a control signals, control some information, it's like controlling some devices, check whether this device is working or not, whether this device is ready or not. So these kind of signals will be generated with this control unit, and that will be made available to other devices. So this CPU, central processing unit, always has some input devices connected and output devices. Input devices, it's like a keyboard, mouse. We will attach this to the microprocessor, will generate, write a program. So information, whatever information we provide it to the microprocessor is in the form of programs. You have written a C programming language, a program in C programming language that has been saved in the memory, and then we say that to execute. Who will execute? The processor will execute. Then this information from a keyboard will be communicated or stored in the RAM is known. We will save this particular program, and then this program, when we say execute, the information instruction by instruction or line by line provided to this central processing unit, it will execute and finally display the result on the output devices like monitor, we have a printer, or some other devices through which we can display or generate the output. So this is how the central processing unit work. Then this is a block diagram for 8086, the internal architecture of 8086. This is not actual, but this is behavioral architecture of 8086. This is how the 8086 microprocessor behaves, works. So as I said, this is a central processing unit, and this is a memory. This is where the RAM is connected, memory. This is where the RAM we have always connected to the microprocessor, and this microprocessor gets the information. See, we already said that the memory will have the programs and the information required for the program. Then this information is collected from a memory or stored to a memory. This is two-way communication. We'll collect the information from a memory using this bus. We have already seen the bus. So bus is a medium, a wires, a communication device through which we will send the information or data from one place to another place. So from memory we will get the information and store this information into this particular queue. So this particular queue is known as instruction queue. So we say this instruction because we are writing a program that is for addition of two numbers, subtraction of two numbers, or etc. anything, any program. So this particular program will have the instructions. For example, get the input from a user, get another input from a user, add these two numbers and display the result. These are the instructions available in your program. So this instruction by instruction, it will collect one after another and store it in this queue. This is a queue data structure. This queue data structure will have this is input and this is output. We can say this add, insert and add operations will be done in this queue. This is a 6-byte queue. Every location is 1 byte. This is 1, 2, 3, 4, 5, 6-byte queue. So there is a insert and delete or remove kind of operation will be done in this particular queue kind of data structure. This is nothing but an internal memory available in microprocessor IC. This is an internal memory, one type of memory. So this instruction will be provided through this bus to the arithmetic and logical unit. But before this arithmetic and logical unit, the information or the data will have to be provided in these registers. So let's say we will be adding two numbers like 0001 and 0002, or say 1111 or and 2222. So this information we need to add 1111 plus 2222. So add is an instruction, whereas 1111 and 2222 is a data on which we are going to process the instruction. So what is instruction? Add is instruction. So this add instruction is provided to arithmetic and logical unit, whereas 1111 and 2222 will be collected from this instruction queue to this registers. These are the registers, storage space available. So this is a 16-bit. So 1111 will be stored here, 2222 will be stored, and the add instruction is provided here. So this add instruction in arithmetic and logical unit will get the 1111 from here, 2222, and add it. After addition or during addition, some results will be generated. So this result will be displayed here, but the result, final result, will be stored in the same AX, the 16-bit register. Then we have some instructions, 16-bit SP, BP, SI and DI. We'll talk about that. We also have ES, CS, SS and DS, IP. These are the some registers which are used in the microprocessor. So these registers are directly involved in accessing a memory, getting information from memory. So through this only we will be able to access the memory. So it will allow to access a memory. Without these registers, the CPU is not able to access the memory. So these are registers known as ES, extra segment, CS, code segment, SS, stack segment, DS, data segment and IP, instruction pointer. So we have, just now we are talking that these registers like CS, DS, SS and ES, code segment, data segment, stack segment and extra segment, these registers allow the microprocessor to access the memory. This is a memory. So this starts from 0, 0, 0, 0, 0. This is an index. This is nothing but an index. the index, this is 0000, then 0001, then 0002. These are the locations where the information is stored. This is a 0000th block, then we have, this is 1, this is 0001th block, then we have second, and so on. So this is how FFFF will be the last space where the memory can be stored, information can be stored. This is space. So these spaces, memory spaces, can be accessible using these address, these locations, these locational addresses 00000 to FFFF. So all this particular space, the complete space, is divided in segments. Segment is nothing but it's a part, a small section of a memory. So each section is of 64 kilobyte. Each section is of 64 kilobyte. So it means the complete memory is divided in different parts. It's a virtual partition will be done. So these partitions are named as a code segment. It's just a name has been provided: code segment, data segment, stack segment, and extra segment. All these segments has their own purpose, or with some particular purpose the memory will be used. So let's assume that we have written a program for addition of two numbers. So this particular program will be stored here. The program is stored here. We want to add two numbers. So these two numbers are made available here. 1 1 1 1 will be stored here in data segment, and 2 2 2 2 will be stored here in stack segment. Sorry, data segment. So program will be stored in code segment. Data will be stored in data segment. Stack will be used during processing of these instructions or a program, and extra segment is used if data segment is full or not enough space, then extra segment will be used. Extra segment will also hold the data, the information. So this is how the complete memory is used or separated in number of segments: 1 2 3 4. We can have multiple segments. It's not only 4, we can have multiple segments. So these segments, then how to access this segment? We know in the hard disk drive we create the C drive, D drive, E drive, F drive, these kind of drives. So these drives will be accessible, made available. How we do it? We have stored the address of that in some location. So that location will have the address of the starting point of that particular drive. So with this we can access. So this is how the starting point of this code segment, is stored in code segment. This is a register. This is a 16-bit register. So 16-bit of information. Let us assume this starts from 0 1 1 1 1. So this particular code segment starts from 0 1 1 1 1. So it will store 1 1 1 1 information here, so that whenever somebody wants to get access of a program written or stored in this memory, he can directly go to this location with the help of code segment, and he will be able to access the information in code segment. Likewise, the data stored here, the starting address of data segment is stored here. Let's assume, say this is a 2222. This is a 2222 2222. This 2222 is stored here. That's why with this we will be able to access this particular space and get use of this particular data segment. Same starting address of this particular location, code segment, will be collected and stored in this stack segment. Same as the starting location of extra segment is also stored in extra segment. So this is how we will be able to get access of these segment resistors very easily. So the job of these segment resistors, code segment, data segment, extra segment and stack segment, will be to interact with the memory. So this is a memory. So this memory is nothing but a RAM. The starting address of this is 0000 to FFFF. In total 1 megabyte of memory will be made available. So this is how we will be able to access the memory into the contents of memory into microprocessor. So this was the block diagram we are talking about. Just now we have studied these segment resistors till this ES, CS, SS and DS, only 4. So these will generate, this will have the address of memory. It will generate the address from where the information has to be collected. So the address is communicated and then the data from that location will be collected using the bus and stored into this queue one after another, and then this information is stored into the registers if it is a data, and if it is instruction then it will be communicated to arithmetic and logical unit for processing. Now we will see what are the resistors available. So the resistors available are general purpose resistors, index resistors, segment resistor and status and control resistors. Segment resistor we have seen, it will hold the address of the segments, code segment, stack segment, data segment and extra segment. Now we will look at the general purpose resistors, say AX, BX, CX, DX, some index resistors, base pointer, then this is index, source index, destination index and this is a stack pointer. Then we have some flags and instruction pointer resistor. So the general purpose resistors are 16-bit resistor, all are 16-bit resistors, 0 to 15, total 16 bits are stored in this resistor. As we said, we have AL and AH. AL is 0 to 8 bit and then AH is 8 to 15, total 8 bit. So this is a 8-bit resistor and this is also 8-bit resistor. In total, this is a 16-bit resistor. So this 16-bit resistor will hold a 16-bit of information, but sometimes we don't want to use a complete 16-bit information. What do we want to use? We want to use a 8-bit information. Then we can directly have access of only AH or only AL. Same for BX. BX is a 16-bit resistor, but it can be used as a BL and BH 8-bit resistor. CX again 16-bit resistor, CL and CH can be used. Then DX is a 16-bit resistor, it can be used as a DL and DH. So these are general purpose resistor. It also has some special purpose. This is used as an accumulator. This is very close to the arithmetic and logical unit. So this is the default storage. Whenever arithmetic and logical unit will generate some result, the result will be automatically stored into AX, accumulator. That's why we call this as an accumulator. Then this is a base resistor. Sometimes whenever the information need to be processed as a base resistor, then this will be used. This is used as a counter. Sometimes when we use a loop, so then this CX will be used, CX resistor will be used. Then for working with IO devices, IO related operation, input and output related operations, then this DX resistor will be used. These are some special uses of this general purpose resistor. Normally, these are used for storing a simple general information whenever it is required. This is accumulator. So we have EX resistor. It has some special processing or characteristic. This is known as accumulator. As I said, it's very close to the arithmetic and logical unit. So this is a default register of arithmetic and logical unit, or this the central processing unit. This is a preferred register to use in arithmetic and logical unit and data transfer instructions. So sometimes we also need to transfer a data. So this will be a default. By default, we will store the information here. So because it generates a shortest machine language code, that's why this will be used. Must be used in multiplication and division operations. This will be automatically. This is very close. That's why it will be used maximum times. This will be in use. So whenever we are working on I/O operations, input and output, whenever we want to send a data to some devices or get the data from devices, then this will be a by default register, always available for processing. Then we said like BX register, this will used as a base register for whenever we are working with some data, then this register will work as a base register. It also serves for generating the addresses sometimes. This is a counter. Whenever we are using loops, then this will be used. It is also used in rotate and shift kind of processing. There are some instructions, the commands known as shift and rotate. In these kind of instructions, CX register will be used. We have DX data. As I said, this will be used for multiplication and division and I/O operations. Next, we will proceed with the pointer and index registers. The pointer and index registers are known as SP, BP, SI, DI and IP. So all these are 16-bit registers. We have a stack pointer. There is a segment. We're talking about the segment known as stack segment. So the stack pointer register will allow you to point the stack. We have already studied stack data structure. So in stack data structure, we have the stack pointer, which points to the current data which has been stored in the stack. So this stack pointer always used for pointing to the topmost information in the stack. This is a base pointer. It's used for processing. Whenever we are trying to manipulate two different data, we are accessing two different locations, then this will be used as one of the pointer. This is a source index, this is a destination index. Sometimes what we need to do, we need to get information from one location and store another location. Sometimes we can say that as a copy, block transfer or content transfer. So the same contents from one location will be copied and stored on another location. So this will be done using source index and destination index register. Source is pointing to the source from where the information will be collected. Destination index will be pointing to the location where the information is to be transferred. So this is how the source index and destination index registers are used. The instruction pointer. This is, we will have the in the memory, if we have some program stored, the programs are as you have written in the C language, maybe get information from a user, store it, add it, then display it. Some of the information is here. So whenever we get this program, provided this program to CPU, then what CPU will do, CPU will get a first instruction. So how a CPU will understand first instruction is here. So this IP instruction pointer will always point to the instruction. This is first instruction, this is second, this is third, this is fourth, this is fifth instruction. This is how the CPU will execute the instruction. The microprocessor will execute the instruction one after another. If this instruction is being executed by the microprocessor, then this IP will point to the second instruction. If this is provided to the microprocessor for execution, right that time it will start pointing to the third. If this instruction is provided to the microprocessor, so it will point to the next instruction. So instruction pointer always point to the program or the instruction which is to be next executed by the microprocessor. This is the use of instruction pointer. In this particular 16, all these are 16-bit register, but this it has to be used as a 16-bit register only. There is no higher byte, lower byte, or 8-bit register can be accessible. This is a complete, the total has to be used. This is an example of an instruction. This is an example of an instruction. So in this example, we have, this is an instruction. This is an instruction. What this instruction says, I will provide one more instruction like move. Move is instruction. It has AX and 1111. This is 1111 information has to be transferred to AX register. AX is what? Accumulator. So in this accumulator, we are supposed to transfer the, this is, it says like move. This is a move. It says move. Move the instruction, move the contains. What contains? 1111 to what? AX. So this is a command, and this is where the register, the information has to be stored. Then I will write another instruction, say move, say BX, and say 2222. So this 2222 information has to be transferred in move the information. What is it? 2222 into what? BX. So this is how it works. So we have got 1111 into AX and 2222 into BX. Then what we do? We will add what? Add AX comma BX. So this will add the information from BX. See 2222 will be added into 1111 and final result is 3333 will be stored in AX register only. So this is how a small program, how it will be executed. So this instruction pointer will start pointing to the first instruction, then second, and so on. This is how it will work. It's a general idea, generalized idea for just for understanding. IP is not directly controlled by a programmer. This is very important. All these pointers can be used by the programmer. He can make use of during this particular program, but we cannot use this particular IP instruction pointer because it will be automatically increased as per the execution of the program will be done. So this is how we understood the working behavior of 8086 microprocessor. We understood that we have got a memory to which the microprocessor will has access and get the information with the help of CS, DS, ES and SS segment pointer registers, get the information into a 6-byte queue. Then this information will be provided to the arithmetic and logical unit for processing. The same, if the data is available, the data will be stored into registers known as AX, BX, CX, DX. And we also studied some of the general purpose registers known as AX, BX, CX, DX, some special purpose registers known as SP, BP, SI, DI and IP. So this is what the structural few part of 8086 microprocessor. The remaining part will be discussed in the next lecture. Thank you.